Hello, my students who need some more help in understanding projectile motion problems. We're going to do 3 today, and so let's get started. We're using our test. So the very first one, a ball is thrown horizontally from the top of a 60-meter building and lands 100 meters from the base of the building. Ignore air resistance. You want to find out how long it was in the air, what was the initial velocity, and what was the final velocity. And we need to think vectors when we answer that problem. So the first thing we did, read to understanding. Second thing is we're going to draw a picture and write everything that we know and don't know. And I'm going to use purple. So here's our 60-meter building. So this is in the y direction, so I'm going to just say y equals 60 meters. The ball is thrown here at the top. So I'm going to put a vector, call it v initial, and I know that it lands 100 meters away. This is in the x direction. Okay, what else do I know about the ball being thrown horizontally is that it is all in the x motion, x-axis motion. So that's also going to equal v initial x. We don't know what that is. We do know that v initial in the y direction is 0. There is no velocity going either up or down. We know time. Well, we don't know time. That's one of the things we're going to find. And then down here, I'm going to kind of redraw it as a vector. And break up the components. Okay, this is not to scale, but here is v final in the x direction. Well, we know because there's nothing moving, increasing our velocity or decreasing our velocity. We're ignoring air resistance. So the initial velocity up here in the x direction is exactly going to be what it is in the y direction. So v final in the x is going to equal v initial in the x. But this one here is v final in the y. We don't know what that is. We do have a final velocity in y because what's going on in y? Well, we have just an initial velocity in x, but in y, something's bringing it to the ground. And that something, of course, is gravity. All right, so here, I think I have everything I know and everything I don't know in written down. So I've read to understanding, I've drawn my picture, I wrote everything I know and don't know there. And now I'm going to look at equations. In my toolbox of equations, I know there's the general one, d equaling, which is distance, equaling the initial distance plus v initial t plus 1/2 at squared. So this is general for x or y, or when you get to 3-dimensional, even in z. So we just use d as distance. So it's just a general equation, but we know that one is going to apply in some fashion in the y direction as well as in the x direction. Another one that's useful is acceleration times time equals delta v. So this one is sometimes really helpful. And I think for this particular problem, those are going to be the 2 main equations that we need. So I need to separate what's going on in x and what's going on in y. So I'll write x here, and I don't have a huge board, so I'll try and put it all on here so you can see. So if we look at what's going on in x, there's no acceleration and there's no initial position. So I just need to write x equals v initial x times time. But we know v initial x is just v initial, so I can actually drop the x there. So that's my equation in x. It's pretty straightforward. All right, and in y, I don't have an initial position. I don't have an initial velocity, so I know that everything in y is going to be 1/2, and the acceleration in y is gravity, gt squared. So in this case, I know my y, I know my g, and I don't know my t. Well, t is one of the things I need to solve for. So I can quickly solve for t. And I've done it. And then when I do my calculations, I plug in my numbers, 2 times 60 divided by 9.8. All right, so up here I said it was negative 9.8. I need to look at where I'm putting my coordinate system, where the origin is. And if the origin is here, so this starts y equals 0, then down here, this is going to be y equals negative 60. So this is actually negative 60 and negative 9.8. Of course, the negatives cancel, and that's great because we're not dealing with imaginary numbers here, especially with time. It needs to be a positive number, and time, when we do the calculations, ends up being 3.5 seconds. So now if we know time, we can now find the initial velocity. So I can solve for initial velocity here. It's x divided by t. So the initial velocity is 100 divided by 3.5. Before we go on, let's just make sure our dimensions are correct. I mean, it should be because the equation falls out correctly like that, but we just want to make sure. So if I look under the square root, I've got meters divided by seconds squared. And of course, when you do the division here, you get square root of the meters cancel out, you get square root of seconds squared, which is just seconds. So that works really well. So we're good there. On this one, we have meters divided by seconds, which is exactly what we need for meters per second. So V initial is 28.6 meters per second. So we found our V initial, which happens to also be our V initial in X. So I just don't want you to forget that, because we're going to be looking at this triangle in just a little bit so we can find the actual final velocity. And we have our time, so now we need to solve for our final velocity. And we're going to use Pythagoras, which is a squared plus b squared equals c squared. And we can see that here it's going to be V initial or V final in the X plus the V final in the Y equals V final period. But we're still short. We have V final in the X, but we don't have these two. So we have this other handy equation. If we're still dealing with Y, so I'm still in Y over here, I'm going to look at this. So our acceleration in Y, again, is just gravity, and it equals delta V, so it's V final minus V initial. Well, cool. V final is 0, so V final just equals the gravity times the time. We now know the time, and if we look at that, that's meters per second squared times second, so we end up with meters per second. So V final is going to be 9.8, it is negative, times 3.5, which is positive. So V final for Y, I dropped the Y, and V final in the Y direction is going to be negative 34.3 meters per second. So you ask, well, why is that negative? And if we made our coordinate system right here is, positive Y, and out here is positive X, our vector is pointing down, so it's pointing in the negative direction. So this makes perfect sense that it should be negative right here. So we have now our V initial in the X, our V initial in the Y. We can now solve for our V final vector, which is right here. But we're missing one other thing to help give us. Vectors tell us two things, right? Tells us magnitude and direction. So we can get the magnitude, but we're going to have to solve for the angle theta. So we'll need our equation for theta. And since I know V final Y and V final X, I'm going to use tangent theta equaling V final Y divided by V final X. So we can get theta. I'm going to erase this guy for just a second. Theta equaling the inverse tangent of V final Y divided by V final X. So theta is going to equal the inverse tangent of V final Y, which is negative 34.3 meters per second, And v final x is 28.6 meters per second. The meters per second cancels out, which is exactly what we want. Remember, the inverse tangent acts on a number. And so we have a pure number here, and it returns an angle for us. And so we can get theta is now negative 50.2 degrees. And we'll come back to what that means in just a second. We need to find room for the other guys. So v final x plus v final y. Did I forget the squareds last time? I think I did. I did, didn't I? Forgot the squares. It's okay. It's okay. We now have the squares because they're there. So v final is going to equal the square root of 34.3 squared plus 28.6 squared, and the square root of that sum, and we end up with v final equals 44.7 meters per second. So we have the answer as time. We'll switch colors for the answer. Time is 3.5 seconds. The initial velocity is 28.6 meters per second. The final velocity, if you look at it, even though it yields a positive number, well, actually when you take the square root, you get positive or negative. It should be negative because it's going down. But we can go ahead and write it as positive, and it's going to be 50 degrees, 50.2 degrees with the ground, the horizon. So it's from here to here is the 50.2 degrees. And there is the answer. And so just to look at it a little closer, we read to understanding. We wrote everything we knew and didn't know. And then we did our equations for x and in y. And we needed to separate what was going on in x and y because they're two different motions, even though it's the same, in this case it was a ball, going down. They're two different motions. What's going on in x is just purely velocity. But what's going on in y is the gravity is bringing it to the ground. And so we can look at them as separate equations that we're solving, but what ties them together is the time. The time it takes to go from here and just drop is going to be the same as the time it takes to go from here and be thrown. And so we have our motion in x, our motion in y, and you notice we went from y to get the time to solve for the motion in x, the velocity that we didn't know. And then we had to come back and find the final velocity in y using our other equations. So really the 3 or 4, if you want to count the tangent equations that we needed, were just right here. And we solved it. Yay! All right, problem number 2. What is the launch speed of a skier that leaves the launch ramp at 63 degrees with the horizontal and attains a height of 13 meters? So we read for understanding, and now we're going to draw our picture. So here's our picture. Here's our launch speed, which is unknown. And it's a vector, so I'm going to break it into its component vectors. Theta we do know is 63 degrees. We got v initial in the x direction, v initial in the y direction. Both of those are unknown. Our skier takes off, attains a maximum height, y equaling 13 meters, and I know g is negative 9.8 meters per second squared because it's a velocity. No, it's not. It's an acceleration. G is an acceleration. It's bringing the skier back down to earth. Keeping it real, man. Okay. We are only concerned with the launch speed, right? The v initial, this vector here. And we could use the x motion to help find it, but I think we can do everything in y. And let's just write down our equations that we're kind of playing with, we have the position, the initial t plus 1/2 at squared. That's our general position equation. We also have that at equals delta v. And in this case, because we're dealing specifically with this vector triangle, we're going to have some trig functions. And so I know a squared plus b squared equals c squared. I know that cosine of the angle is the adjacent divided by the hypotenuse. I know that the sine of an angle is the opposite divided by the hypotenuse. And then there's the tangent, which is the opposite over the adjacent. I don't really think we need that one either. So let's write down what we see going on in y. Well, we can write down our general one, y equaling, there's no initial position, so we can ignore that, but there is an initial velocity, vi initial in the y, or v initial in the y, times time, plus 1/2 gt squared. All right, so we have time that we don't know, and we're not really looking for it, so we don't really care about it. Well, we do care about it because we need to solve the problem. But we also have the initial position, the initial velocity, which we don't know. But we have another equation. So gt equals v final in the y minus v initial in the y. Well, if we look at that, it looks like we've gotten another unknown, but if we recall, this is at the apex at 13 meters. So v final in the y is going to equal 0 at the top. So that goes away. So we get gt equals negative v initial in the y. We can divide both sides by g, solve for t, and then substitute that into our main equation. Because again, it's not t that we're looking for. So it'd be nice to get rid of that v initial y divided by g. So I'm going to take that, substitute it in here, and I get v initial y, negative v initial y divided by g, plus 1/2 g negative v initial y divided by g, the whole thing squared. And then we're going to simplify down, negative v initial y squared divided by g, plus 1/2 v initial y squared divided by g. Combining that, I get y equals negative v initial y squared divided by g. And I'm going to solve for v initial in the y direction. So I'm going to move that over here. So v initial in the y direction is going to equal the square root of, I forgot a 2. There we go, because negative 1 plus 1/2 is negative 1/2. Yeah, so there we go. So I got 2y divided by g, and that quantity is negative. And now I'm going to come right here. V initial in the y direction equals the square root of negative 2 times 13 divided by negative 9.8. And we do that, I get v initial in the y direction equals 16 meters per second. Okay, this is helpful because now I have this guy. And honestly, if I have this guy and I have the angle, I can now solve for the initial velocity. So v initial is going to equal, well, let's see, first of all, before I write that, what trig function, if I know the opposite and the hypotenuse and the angle, I'm going to use sine. So sine theta is going to equal the opposite divided by the hypotenuse, v initial y divided by v initial. I need to solve for v initial. So v initial equals v initial in the y direction divided by sine theta. I just used the cross multiplication thing. So v initial is going to equal 16 meters per second divided by sine of 63 degrees. V initial equals 18 meters per second. And this was what we wanted to find out. There you go. Straightforward. All right, problem 3, our last in our projectile motion. So we did one where a ball was thrown horizontally off of a building. We did one where a skier starting from the bottom of the hill was launched off onto a slope. And now this one, number 3. An arrow is shot from the height of 1.5 meters towards a cliff of height y cliff. It is shot 30 meters per second at an angle of 60 degrees. It lands on top of the cliff 4 seconds later. We want to know, what is the height of the cliff? What is the maximum height reached by the arrow? And what is the arrow impact speed hitting the cliff? So, read to understanding. Now let's draw a picture, because this one's a little more involved. There's some things we actually don't know. So here we have, it is shot from a height. So it actually has an initial position, doesn't it? At 1.5 meters. It's also shot, if I put horizontal there, the V initial is shot at an angle. The angle happens to be 60 degrees. We know G is negative 9.8. Okay, so we know the arrow is going to travel up till it reaches some apex up here. And I'm going to put that the V final and the Y is going to be 0, just to say here's the apex. And then it's going to come down. Here's what we don't know. We don't know where the cliff is. If this were to just come down to the horizontal here, it would impact somewhere here. Is the cliff above there or below there? And just because I have to choose something so I can make my drawing, I'm going to choose that the cliff is actually above it. So here's Y. Ooh, that's a bad color there. I'm supposed to get rid of that. Go back to purple. This is going to be Y cliff on YC. Okay, so from here to here, this is the max for this horizontal. So this problem does have some problems. There's some issues with it because there's a lot going on. Let me come back to the cliff because we also have the impact. I'm going to draw my vector here, V final, and I'm going to draw it into its component vectors, V final Y and V final X. So the question is, let me draw these component vectors as well. V initial X, V initial Y. Is this initial velocity going to equal this final velocity? If it landed here, the answer would be yes, but the V initial actually would still be, the velocity in X is still the same, no matter where it is, because there's nothing in X slowing it down or speeding it up. The velocity in Y, though, does change, so it's not going to be, like the V initial here, if it were to go all the way over there, it'd be the same, just the opposite direction, because now it's coming down. But in this case, the final velocity is not in any way resembling the initial velocity because we don't exactly know where this cliff is. But I'm going to guess it's above the horizon. I'll just erase this stuff too. All right. Is that everything we know and don't know? We know time to this point is going to equal 4.0 seconds. But that time is not the same as the time up here. So I'm going to put time at the top, time t. Time top is unknown, because we actually don't know that time. We can find that time really easy. And knowing this time will help us know where the cliff is. So for instance, if this time is 2 seconds, we know the arrow travels for a total of 4 seconds, so that tells me the cliff is the same height as its initial velocity. If this time is 1 second and it goes 4 seconds, well then we know the cliff is down here. If this time is, say, 3 seconds and it travels for 4 seconds, we know the cliff is above the horizon. So finding this time will let us know where that cliff is. And so it'll be very, very helpful in finding that. All right. We also have this little segment right here. I'm just going to call that delta y. So y cliff is going to actually equal to this initial velocity, initial position right here, plus this itty bitty bit We don't know how much delta y is going to be. The other thing we were asked for is the height of the arrow at the top there. So y arrow, the maximum height the arrow reaches, is going to equal, again, this initial velocity plus this y max. So because I wrote this way, I'm going to make my coordinate system kind of start here. I'm going to make that the origin, right? Because when I do the equations, it might just be easier to ignore this initial position while I'm finding some other things, and then throw the initial position in at the end. When I need to find those two things. So what else are we looking for? So we know this angle. We don't know this angle. I'm going to call it alpha. Right? And we might need to find it. We should find it so we know, because vectors give us magnitude and direction. It's a good idea. All right, are we ready to solve this problem? This problem is going to take the whole board and then some. So now we need to figure out what is our motion in x and our motion in y. Right here, let's look at these two, because we can actually solve right away for what v initial x is. V initial in the x direction is going to equal v initial cosine theta. V initial in the y direction is equal to v initial sine theta. So that's some more things that we know. I won't write our general equations because I think we're going to need every bit of board space I can get. So here we go. Y. Y max, which is this part right here, is going to equal, it would equal like this if I wanted to draw y max as this whole thing here as y of the arrow. I'm going to actually not do that right now. That would be y arrow would include this initial velocity plus that. But I'm just going to ignore the initial position just for a bit, because I think it'll make solving a little easier. So I'm just looking at this. So y max goes from here to here. Equals v initial y t plus 1/2 gt squared. So two things are affecting the arrow's motion in the y direction. It's the initial velocity and the gravity. All right. I also know delta v in y is going to equal gt. And so I'm only concerned right now with my work to the top here. So it's going to have a v final in the y minus v initial in the y is equal to t. I'm going to stop there with y for a moment. I have two equations in my y, and I'm going to look at x. X equals, the only thing really moving in the x direction is just that initial velocity. The initial x t. So knowing what the initial xt is, I'm going to go ahead and put it in the initial t sine theta. I write the t in front of the sine theta just to distinguish that the t is its own number. It's not part of sine. The sine at the end, because sine is only working on theta. I do know v initial. That's 30 meters per second. So I know v initial. I don't know the time at the top, but I do know the time all the way over here if I wanted to solve for where it ended here. So right now I'm going to leave that alone. Or we could just go ahead and solve for how far out it goes. 30 times 4 times sine 60. So in this case, this is 60 meters. So right here, this position, x equals 60 meters. I don't know as if we need it, but we'll put it up there just in case we do. Okay, I wrote x is 60 meters right here, so I'm going to erase that part of x right now, and I'm going to come back to my motion in y. I kind of want to use these two equations and do what we did last time, and this time though I want to solve for t, because I want to know what this height, I want to know what time is at the top of this. So at the top, v final is going to be 0. So negative v initial y is going to equal gt. So t is going to equal negative v initial y divided by g. Well, I know v initial y is I sine theta, so t equals v vit sine theta divided by g. So I know vi, there's not a t there. Oops, okay. I just got happy with my t. V initial sine theta divided by g. I know v initial, I know sine theta, and I know g, so I can plug all those in. T equals, let me rewrite it here. T equals negative 30 sine 60 divided by negative 9.8. T equals 2.65 seconds. All right, so if at the top this is 2.65 seconds, it's more than half of, or wait, how do I say that? Twice this would be 5.30 seconds, which would mean the endpoint is here. So the cliff, I did draw it correctly, the cliff is above the horizon there. All right, now that we know the time up here, we can work towards finding the height of the cliff. Oh wait, we can actually find the y max. Let's do that. So y max equals v initial t sine theta plus 1/2 g t squared. So I'm going to use this for the t, for the y max. I know v initial is 30, and I know the angle. So y max equals 30 times 2.65 times sine 60 plus 1/2 negative 9.8, 2.65 squared. And hold on, I gotta find that one. Because I did it. So it'd be 34.5. All right, let's get the calculator. I solved it different. Okay. Entered 2.65, multiply, is my thing okay? 2.65, 9.8, I'm going to multiply, 2 divide, add. Did I say 34.4? I did. Okay. All right, so this y max equals 34.4 meters per second. So now we have this guy, y max, and I don't have a place to write it, equals 34.4 meters per second. All right, so we're getting there. We need to find the height of the cliff. We need to find the maximum height reached by the arrow. So having this, I can now find the height of the cliff and the height of the arrow. And we also want to know the impact speed as it hits. So let's find the y of the cliff is going to equal, we don't have that part yet, y of the arrow is this plus this, so it's 35.9 meters So delta y, this little bit right here is, I have to do that. Okay, delta y is going to be our main equation at 4 seconds. So I'm going to put a little parentheses at 4. And what that tells me is when I release the arrow and I let it travel, recalling y initial plus v initial t plus 1/2 at squared, this is traveling and at some initial position at some velocity with some acceleration for 4 seconds, meaning it's going to land here. So that's the y at 4. It's going to equal v initial t sine theta plus 1/2 gt squared. So I'm going to plug in 4 for the time. So the delta y, this part right here, is going to equal 30 times 4 times sine theta, which is 60, plus 1/2 negative 9.84 squared. Let me rewrite that over here so there's room. Delta y equaling 30 times 4 times sine 60 plus 1/2 negative 9.8 times 4 squared. Delta y equals 27 minus, well, we can go ahead and solve for the cliff if we add. So y of the cliff is going to equal y naught plus delta y, which is right there. Y of the cliff equals 27.0 meters. So all I did is plug that in and then added 1.5 to it, and I got 27.0 meters. And so now for the impact velocity, we know the v initial velocity, we know that. How do we find the impact velocity over there? Went to the second page, so I have to erase some stuff here. All right, for the impact velocity, I know v final in the x is going to equal v initial in the x, which equals v initial cosine theta. So v final x equals 30 cosine 60. V final x equals 150 meters per second. V final in the y direction is going to be delta v in y equaling gt, and this is t at 4 seconds, because again, we're only going to here. We're not going all the way. That's going to be v final y minus v initial y equaling g at 4 seconds. V final y minus equals gt plus v initial y. V final y equals gt plus v initial sine theta. Sine theta. Now we can plug in the numbers. V final y equaling negative 9.8 4 seconds plus 30 sine 60. V final y equals negative 13.2 meters per second. So now we have v initial, or v final x, v final y. We can use Pythagoras theorem. So v final is going to equal the square root of v final x squared plus v final y squared. So the vector v final is going to be square root of 150 squared plus negative 13.2 squared. That equals 20 meters per second. And then theta is tangent theta equals, well, oops, it's not theta, it's alpha. Alpha is going to be v final y divided by v final x. Alpha equals the inverse tangent of v final y divided by v final x. So alpha will equal the inverse tangent of negative 13.2 divided by 150. Alpha equals negative 50.4. So our final velocity is 20 meters per second, and it's within 50 degrees with the ground. So it's kind of a long problem, but we got it done. And that's how you solve three types of projectile motion problems. All right, looking at projectile motion problems, we're looking at just a couple of very simple equations and what's going on in 2 dimensions, because our projectile motions are only 2-dimensional right now. And so I want to just do a general, here's a projectile motion, right? This is the horizontal. All right, we're not going to have any initial positions in my general equation here. So this is y, this total is x, I'll just put it right there. And we have an angle theta here. And we have an initial velocity going on here. And we know that constantly tugging down, no matter where the projectile is, always bringing back to the ground is gravity. It's always bringing it back to the ground. And everything gets broken down into vectors. And in this case, the v initial and the x is always the same as it's going all the way through here, right? The v initial and the y, though, it's shrinking until it comes to v final in the y at the top, which is 0, and then it begins to increase again, but it's pointing the other way. So here, v final in the y is pointing in the opposite direction. And there's v final in the x. All right, so we always want to look at what's going on in x and what's going on in y, and that's why we separate motion in x with motion in y. Or you'll hear other people say the horizontal motion with the vertical motion. And the equations are the same, and if you understand what the equation is telling you, then you know what's going on. So I could write x equals the initial position plus the velocity plus the acceleration. But I know, in this class anyway, we don't usually have an initial position, so we can ignore that. And there is no acceleration acting on it, so x is always going to be pretty simple. It's just the velocity and the time that it takes to complete its course. Y is a little different. Might have an initial position, squared, but gravity is always acting on the vertical motion on y. Gravity is always bringing that projectile back down. Now here's where, in this is where the trig comes in, because v initial in the x is going to always equal the vector, v initial cosine theta. V initial in the y is going to equal, again, the vector, v initial sine theta. I forgot to write that one down in the y. And so these will help you solve them. And the other thing that's going on really with x, that's pretty much all that's going on. What ties the two together is time. Time in x is going to be the same as the time in y. But the other equation that can help you is gt equaling delta v. And we've actually used it in these examples we did today. Those can help you narrow down. So when you're looking at a problem, it doesn't really matter what you're given and what you're not given if you can let the equations speak to you as to what they need to get solved. If you're not given the initial velocity, it's okay, because you can use the different equations to help you find them. If you are given the initial velocity and virtually nothing else, you can again use those to help you find what you're looking for. There's plenty of equations that you're given to help you solve what you need. So I really hope this helped. I really hope I went slow and methodical. You know, we want to be logical, and this is why I impress that you separate what's going on in the horizontal, what's going on in the vertical, so you know what the equations are telling you and how to solve them. And that we solve them algebraically first before we start plugging numbers in, because then you can see how things are going and where you went wrong. It's really, if you went wrong, you might not have gone wrong, but it's really important to be logical in your processes. So, thank you.